Oh, hi guys, welcome. This is a lecture that's going to help us get into Unit 9, which is the last unit of AP Chem. I'm still in the process of grading your tests and stuff for acids and bases. So as soon as I know the final thing, I'll let you know if there's recovery questions. And anyway, good job with that. So today we're going to meet entropy, which is fondly represented by the letter S. And in this unit, actually, we're going to put a lot of things together. We're going to put some thermo together with some equilibrium and see what happens to systems. And so if you remember from the thermo unit, we had met enthalpy, which is H or delta H. And if the delta H of a system was negative, the process was exothermic. And if the delta H of a system was positive, we had an endothermic reaction. Ugh. So we're going to come back to that. But let's meet entropy. Basically, entropy is a measure of the disorder of a system. And it's kind of counterintuitive because the entropy actually increases or is positive the more disorganized something becomes. And so if we have a positive delta S, what that means is that the system is more disorganized. And if we have a negative delta S, the system is actually more organized or neater or more uniform. And in biological systems and in chemical systems, a greater degree of disorder is favorable. And so the universe favors a positive delta S. We can calculate delta S. We can look at the entropy of the products, the total entropy of the products, and subtract it from the total entropy of the reactants. So increases in entropy are favored. It requires a lot less energy to not clean your room. So a messy room requires less energy than a neat room. It's going to take some energy to clean it up. This one's a favorite of mine, the impossibility of maintaining a perfect lawn. My husband's a huge lawn guy. Takes lots of energy to maintain that perfect lawn. Looking at the laws of thermodynamics, we have already met the first law of thermodynamics, which says that the energy within the universe, it cannot be created or destroyed, but it can be changed from one form to another. But basically, we can look at the second law of thermodynamics to see that the entropy of the universe is constantly increasing. So when an exothermic reaction takes place, the energy is going to flow from the system into the surroundings. Once it's in the surroundings, basically you can't get 100% of it back. It cannot all be reused. So whenever energy is lost to the surroundings, the entropy of the system or of the universe, of the surroundings, actually, the entropy of this system increases. Some processes in which the entropy is positive include melting and vaporization. So those are some good vaporization. You can think of boiling if you boil something, or change it from the gas, from the liquid phase to the gas phase. Also, if we have more particles as products than we do as reactants, that is another instance in which the entropy has increased or the system has become more disorganized. Anytime we add heat, anytime we increase the volume of a gas. So let's take a look at some of those. All right, here's our change in entropy when we are going from a solid to a liquid. So notice our solid is super organized. And then if we look at from a solid to a liquid, basically we have disrupted some of the intermolecular forces, particularly the hydrogen bonding. And our system becomes less organized. And the less organized we are, the more positive the entropy is. Notice then if we go from a liquid to a gas, we become even more disorganized or freer, let's say. So the forces of attraction between the molecules in the gas phase are very weak, so they spread out. And as a result, the delta S is super positive if you compare the products, which are the gas, to the liquids. Our delta S is also going to be positive when the products have more particles. So notice we have two different phases here. So there's two things at play. Our delta S is going to become more positive already because we're going from a liquid to a gas. But notice over here we have 4 particles, and here we have 6 plus 12 plus 10 plus 1, so we have 29 gaseous particles. So not only do we have more particles, but we have more particles that are in a phase that already increases the entropy. So the delta S of this system is definitely positive. Delta S is usually positive when we make solutions with solids or liquids. So here's our nice little organized ionic compound. When we dissolve our ionic compound in water, the molecules are dispersed further apart. They're usually surrounded by water molecules, but the same ions are there, but they are much more disordered. And because of that, our delta S is usually positive. Except when we put gas into a liquid, like let's say with any carbonated beverage and things like that. So if you think of gases are probably the freest example of disorganization. They move around, they're very far apart, they have a social distance that's acceptable. And so if you dissolve a gas in a liquid, the entropy will actually decrease. The system will become more organized. And so the delta S in this case is actually negative. When heat is added, the delta S is actually going to increase. As heat is added, in this case, basically the movement of the particles becomes greater. When we increase the temperature, we increase the average kinetic energy. When we increase the average kinetic energy, the particles move faster and faster and faster. We can disrupt the intermolecular forces, and the particles can become more disorganized, which will actually increase their entropy. This graph is called a Boltzmann distribution graph. And from this graph, we can see that the amount of kinetic energy contained by the gaseous particles within a system is going to broaden as the temperature increases. So this is going to be true for liquids and solids, but it's especially true for gases. If you increase the volume of gas particles, then those gas particles are able to move about in a much bigger space. There are more potential hits and arrangements, and so there's actually more disorganization, kind of freer. I always think of, is the system freer? Then the delta S will be positive. So let's look at how to calculate delta S. Delta S is going to be the sum of the S of the products, or the entropy of the products, minus the sum of the entropy of the reactants. And you'll either be given these values, or you'll be able to look them up in a table or in an appendix of your book and things like that. So let's look at a couple examples. This says calculate the delta S for the following reaction at 298 K, which is 25 degrees Celsius. And so I want you to take a look at it. Everybody's in the same phase. We're gases. And we have 3 particles of a gas. We're going to 1 particle of a gas. So what do you predict will happen to the delta S of this reaction? So think about that. Remember, if it's becoming more disorganized, we'll have a positive delta S. If it's becoming more organized, we'll have a negative delta S. And so our delta S at 0 in this case, our products, we have N2O4, so we have 1 of those. So we're going to take 1 times the whatever the enthalpy of N2O4 is. Minus 1 times the enthalpy of whatever the N2 is, plus 2 times whatever the standard enthalpy of the O2 gas is. And for the purpose of our lecture, I'll give you that. So if we have 1, the standard enthalpy of N2O4 at 25 degrees Celsius is actually 304.2 joules per Kelvin mole. And then minus 1 times the standard enthalpy of nitrogen gas at 298 Kelvin is 191.5, plus 2 times the standard enthalpy of oxygen at that temperature is 205.0. And so our standard enthalpy in this case is a negative 297.3. The units for that are joules per Kelvin mole. And look at this value. Does it make sense? We have a negative delta S. That means our system actually becomes more organized, and hopefully you can see that. You have less particles over here, and so you can see where the system actually becomes more organized. If we're more organized, we're going to have a negative delta S. Another example, we have water as a liquid to a gas, so we are looking at vaporization. And we will predict that process to have a positive delta S. So let's see if at 298 Kelvin or 25 degrees Celsius, it actually does have a positive delta S. And so our delta S0 here is going to be our product. And so our product is going to be 1 times the standard enthalpy of H2O liquid minus that's the gas, because that's going to be the products minus reactants. And then 1 times the standard enthalpy of our water as a liquid and the delta S then 1 times 188.72. That's our product, our gas, minus 1 times the entropy of our liquid, which is 69.94. So our delta S here is 118.78 joules per Kelvin mole. And we can see that our delta S value is positive, which is what we expected if we do a phase change from a liquid to a gas. So you guys should be ready to try problems 1 through 3 and then 5 through 6. Upload your work to Canvas, and then after the due date of midnight, I will post an answer key and you can check your work. And then again, if you have any questions